Hello everyone and welcome back to a new video in programming the finite element method using MATLAB. In this video we are going to continue our solution function by programming the contents of the solve linear elastic function. Just to remind you, we are in the structural analysis function in which one of the paths is the solve linear elastic function, and we are currently standing at the apply loads. So we're going to talk about how we're going to apply loads. Now of course, this is part of a multi-part series about the finite element method, which I will be linking on the top right, and its own programming playlist, which is also linked on the top right. Before I start, I want to mention that every single line of code is available to my dear channel members. However, if you are not a channel member, then don't worry, because you can write along, as every single line of code is shown in front of you, and then you would have basically a carbon copy of my own code. So with that being said, let's talk about apply loads. So sit back, relax, and enjoy the show. Okay, so what is the meaning of apply loads? Well, we have defined a lot of types of loads. We have nodal loads, we have distributed loads, we have bar forces or loads that are applied somewhere on the bar, and those need to be transferred onto nodal loads. Some of them are ready to be transferred. For example, a nodal load is a one-to-one transfer. You can just apply it. But if you have, for example, a distributed load, then you have to replace the distributed load with its equivalent nodal loads, and you have to store it for post-processing reasons. So this apply loads is necessary because we're going to have both nodal loads and distributed loads and bar forces, so we need to deal with it. So let's dive into it. I'm going to basically cycle through every single load case. So here I'm going to say load case index, and this is going to equal from 1 to the length of the object dot, I think it's called load cases, right? Load cases, str load cases, I forgot. Str load cases, there we go. Yep, this is in the controller. We're going to cycle through each one of those things. Now, of course, before I start cycling through, I'm gonna try find all the nodal loads in that load case and all the distributed loads in that load case and so on. So I need a list for those. I'll make me a list of nodal forces. This equals an empty list. I will make me a list of linear loads, and that's an empty list. Maybe I should call it linear concentrated. By linear concentrated, I mean the bar forces that are somewhere in the middle of the bar. And of course, I have the linear distributed, which is also an empty list. Okay, now let me fish out the load case. So load case, this equals the object.strLoad cases of the load case index. Okay, so we now have our load case. Now I'm going to cycle through every single nodal load and see if the nodal load has been applied on that load case. Because remember, I have multiple loads. They might be applied on different cases, and I need to apply them in their corresponding cases. So now I'm going to turn me a for loop here, and I'm going to basically cycle through, and I don't know what I should call it, I equals 1 to the length of the object dot, I think it's called str nodal loads. That's right. So I cycle through them. And now there is an if statement I need to check. So if, now let me fish it out first of all. Let me say here, load equals object.strNodal loads of I. Okay, now I have the load. So if the load dot, let me check. I hope that I'm keeping tab of the load case. Where is the str node? strNodal load. I hope I'm keeping track of it. Yeah, there we go. It's load case ID. So I'm keeping track of it. Meaning if the load dot, wait, I forgot. Is it load case or str load case? It's load case ID. So if load case ID equals the load case dot ID, this means that indeed it is part of the load case, then I'm going to add it to the nodal forces by using my strange way of saying old nodal force equals new nodal force and the load. Now MATLAB hates this because it doesn't like changing the length of that thing. However, I have no option because I don't know exactly how many nodal forces are in that load case. So that's why I have only one option, which is basically to add it to the list. Fantastic. This would end here. Now I'm gonna go through the other load types because I need to fill them out. So here I'll just Control V and Control V. This time it's gonna be str linear. What was it called? Str what? Str line load concentrated. Yes. And I'm gonna fish it out and nothing changes. And nothing changes here. We're gonna check. But now we're gonna add it to the linear concentrated. Okay? And then now we're gonna go to the str line load distributed, this one. So str line load distributed, now we need to fish the load out, we need to ask about the load case ID, and then we need to add it to the nodal or linear distributed. Now I'm surprised why there is a line here but there isn't. I should put S here and shift enter to change the other ones, and S here and shift enter to change the other ones. I don't know why he hates this and likes this. It's the same thing, right? So now we fished out the loads. We basically filter them out, and now, okay, let me just put some commentary here. Here I will say, filter out the loads that are part of the load case, just to declare. And now here, apply those loads. So how do I apply those loads? The easiest part is, of course, the nodal loads. Here I'm going to just run a loop for I equals 1, 2, the nodal loads or nodal forces, and by the way I should say length of nodal forces. So I'm running a loop through the nodal forces that I have filtered. Let me fish the load out. Let me call it nodal concentrate, just the name, and we fish it out from the nodal forces. I should say nodal loads, by the way. This is the more accurate way of doing things because it's not a force, it's a load, it could be a moment. Why do I call it force? I think I should call it load. So loads, shift enter. Okay, fine, now this is more accurate. So nodal constant is going to be nodal loads. Every load has a list that it is applied to, and we're going to cycle through the list because we're going to apply it to every individual str node. So this is going to be a little bit tricky. First of all, I'm going to cycle through a for loop. And here I'm going to say for j equals 1 to the length of. And now I will take the nodal concentrated and get out the applied to. Okay? So we are cycling through all the nodes that were used during the application of the nodal concentrated load. Since we're cycling through this, I'm going to take the node ID first. I'm going to fish it out from the nodal concentrated dot applied to of j. So this is now the node ID. Now the node ID, believe it or not, doesn't give me the degree of freedom because it's the fem node that gives me the degree of freedom. So it doesn't work like that, which means first of all, I must get it. How do I get it? Should I run a for loop? I think for the node ID, I need to run a function for this. So give me a second. I'll first of all say str node equals controller or object dot get str node. Okay. And I'm going to ask it to basically use the node ID in getting the str node. And then I'm going to basically get the fem node by going to the str node and getting the corresponding fem node, because I will use it to apply the load, because here we're going to use its ID to find the degrees of freedom. As a matter of fact, let me do it for you here. So here, I'm going to first of all declare and say that object, which is the controller, dot global load matrix of. Now here I need the degree of freedom and the load case. The load case is easy. It should be the load case ID, right? Or load case index, load case index. So here, I'm going to basically write here, comma, load case index, because the columns are going to be the load cases. However, I need the degree of freedom. Now, how do I do that? If this is node 1, then its degrees of freedom is going to be from 1 to 6. If it's node 2, it's from 7 to 12. So that's actually very easy. Say femnode.id minus 1. Multiply this by degrees of freedom. I think I have it as a constant. I don't have it as a constant. I just multiply by 6 because that's something we should know. And minus 1. This will give me the starting degree of freedom. Let me here put plus 0, first of all. And this is going to equal. So we have now the x force of that degree of freedom of that node. And we're going to add to it. So we're going to use it again. So this equals it, the old self, plus the new value. Oh, this is a very long command. Let's put here ... to push the enter key. And here, so this, the new one equals the old one plus ... enter. This is just to make it one sentence. We're going to add to it the fx. So here, I'm going to go for the nodal concentrated, the load, take the fx out of it. So we're taking the fx and adding it to the global load matrix at the correct degree of freedom. Yep, that's what we're doing. Let me just make sure that the fem nodal load, str nodal load has fx. Yep, it has fx. So everything seems to be fine. I need to do this 5 times because I have fy, fz, and whatnot. So I just control paste, control paste, control paste, and so on. So that is how we apply the nodal loads. However, there is one caveat. There's the get str node from the node ID. I haven't programmed it yet. So I need to go very quickly on the top and the definitions. Let's just put str objects here. And here I will call function node equals get str node based on the node ID. That's what I'm going to program here, right? Because I call this function here. So I need to program it. There are multitude of ways of doing this. I'm just going to run a for loops here. Although it's going to be not that efficient, but I'll keep it. So for I equals 1 to the length of object dot, wait, I did not pass in the object here. So object dot, no, comma, object dot str node. Okay, end. And here, I'm going to basically ask a question. If the object dot str node, you know what, let me fish it out. Target equals object dot str nodes of I. So we are fishing out the node. Then we ask if target dot id equals the node ID that we passed in. This means we got our target, and all we have to do is to set node equals target and then return. Otherwise, if we don't find anything, I'm just going to return empty. So node equals empty. This should never happen, but I need a failsafe nonetheless. So this is how we get the str node, and I think we're doing something. I think we are okay. This is for the nodal loads concentrated. Now we need to go for the other thing, which is, let me just make this smaller. And now we need to go for the next type of load, linear concentrated loads. So for I equals from 1 to the length of linear concentrated. Once again, we need to repeat and rinse the same steps. Here, I'm going to fish it out. I just call it bar force, despite the fact it's not a force. But I'm kind of running out of blank here. I don't know exactly what I should call it. So I'm just going to call it bar force. And I'm fishing out at I, I'm selecting it. And now, of course, I need to run through all the applications. Similarly to the nodal load, right? We ran through the application. So we need to do the same thing for the bar. So here I'm going to go for a for loop. For j equals from 1 to the length of the bar force dot applied to. I hope I have the applied to programmed in the linear concentrated. Let me just check. Linear load concentrated, applied to. Yep, that's the case. So now we can run cycle through it, which means now I can fish out the line ID. And this equals, I don't know, bar force dot applied to at the jth index. And now I need to get the line. So str line, my target line, is going to equal the controller dot get line or get str line at the line ID. Now I haven't programmed it yet. I'm going to program this right now. So I'll go to the top. I'll copy this entire thing and paste it. Maybe I should paste it after the line definition to be kind of consistent. And this here I will call it line. This is get str line. And here, of course, I'm inputting the line ID, which means now I will run a cycle through all the str lines. I will select the line. I will check if the target line matches with the past line ID. If that's the case, I'm going to set the output to be the target and return. Otherwise, I'm going to set the output as nothing and return. So now we have a get line function using the line ID. So now here, there is no error because I just programmed it. Now we have our line, but that's not enough. Oh, this is going to be spicy. I need to know exactly on what fembar it is. Let me explain it for you. There is an str line, and there is a bar force on the str line. Now the str line might be meshed into different pieces. So one str line might contain multiple fembars. Now there is a bar force on the str line. However, the bar force is not applied on all the fembars, or because the bar force might affect only one of those fembars. So now the question becomes, how do I distribute this on the fembar? And more importantly, is this load even affecting a certain fem bar? All those questions need to be explained and need to be done to apply a bar force. So we need to think about it. I must run through a cycle of all the fem bars in the STR line, and I need to apply the bar force to it. And in my application process, we're going to ask the question, is the force even affecting the fem bar? If it's affecting it, I need to calculate something called the equivalent nodal forces. Otherwise, I can go to the next fem bar. We need to cycle through all the fem bars. Now, I hope to God that I have them stored in STR line. I have them stored in STR line. What a lucky thing. So here I will go for k equals from 1 to the length of the line dot fem bars. Now, did I fish out the line? It's called STR line. That's one way of doing things. Alternatively, run a loop through all controller.fembars and check the corresponding STR line. That's another alternative. I might reach for that if that fails. For now, I'm going to run through the fem bars. So here, let's fish it out. Fem bar equals STR line dot fem bars of k. We fished it out. Now here, that's going to be fantastic. I need to fish out fem node 1, which is basically fem bar dot fem node 1. I think that's how it's called. And fem node 2 equals fem bar dot fem node 2. And here the magic should happen. I will say in the following things, I need you to first of all calculate the equivalent nodal loads and then apply the equivalent nodal loads. Now that's something for another video. But those are the steps I need to do. But that's not everything. Because now I need to do the same thing. The entire same brouhaha with the distributed loads. For similar reasons. Because distributed loads might affect multiple fem bars or a single fem bar. And my brain is melting now because I'm thinking how I can do that. I just take for now the linear distributed. Wait, did I blunder something here? I think I blundered something. I should take the linear concentrated. What gives? Here. And now I take the linear distributed. I blundered something, I just realized. Now here, this we will call bar linear distributed, maybe? Okay, so we're taking the load out. We are cycling through the applied tool. We are fishing the applied tool out. We are fishing the STR line out. And then we're preparing it. Yes, this is how it's supposed to be. So now here I have to program something called get equivalent nodal load. So what I need to program in the future is the equivalent nodal loads. This is going to take some time, but we're going to do it anyway. So I think we have reached another milestone yet again. So with that being said, I want to finalize my video. That's everything I wanted to talk about today. I hope you enjoyed. And in the end, I want to give a STR linear load size shout out to my dear channel members in the contributor level and the helper level whose names are going to be shown on the screen. I want to thank them from the bottom of my heart as their support of the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on, especially subscribing because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video. Bye bye.